All right. Hello, everybody. Welcome back to lesson 6. We're going to pick up where we left off yesterday. So still continuing this idea of motion in 2 dimensions and tying position, velocity, and acceleration together, both graphically and today mathematically. So you guys, if you watched the video yesterday, you should have kind of ended up with this problem, this bonus. Give it a try. So here we had a position time graph. And your challenge was to sketch the velocity time and acceleration time graphs from this position time graph. So before I show you guys the answer to this, I want to first talk through a couple of key bits of information that we can learn from this graph. So just to kind of get your mind thinking and get in the right frame of thought for today, I want you to take a minute and think through some of these review questions based on this position time graph. I'll give you about a minute to answer as many of these as you can, and then we'll come back together and talk through the answers. All right, so let's think through some of these answers. Sorry if you didn't get a chance to answer all the questions. That's all right. You can come back and think through them together as a class. So at what times was the particle at rest? Remember, that's going to be wherever in the graph the position is not changing. It's a constant position over a certain amount of time. That means it's at rest. So that happens from 0 to 2 seconds, and then from 7 to 12 seconds, and then from 16 to 18 seconds, and then from 19 to 20 seconds. So those are all the positions that are not changing. That's when the particle's at rest. Number 2, when was the particle moving in a positive direction? So that would be whenever we're dealing with a positive position. So that would be from, well, I guess not necessarily a positive position, but a positive slope of our position graph. So that would be from 5 to 7 seconds, it's moving towards the positive. And then here, from 14 to 16 seconds, it's moving towards the positive direction. And then there, from 18 to 19 seconds, towards the positive direction. So on the flip side, when is it moving in a negative direction? Here, from 2 to 5 seconds, and then from 12 to 14 seconds, it's moving negative. The total distance traveled over that 20-second interval, you would add up all of the changes in position, not taking into account that some of them are negative. We're just dealing with distance, so that's a scalar. We don't care about what direction it's moving. So if we add up all of the position changes, that would give us 22 meters distance traveled. But if we look at the displacement, remember that's the position change from where you start to where you end up. So we're starting in a position of 0, ending at a position of 0, which means our net displacement is 0, even though it traveled 22 meters. What is the instantaneous velocity, magnitude, and direction of the particle at 4 seconds? So 4 seconds is right here. So we need to find the slope of that portion of the line at 4 seconds in order to find the instantaneous velocity. And if we do that, calculate the slope, that gives us an answer of -1 meter per second. Remember, negative implies a direction, but we could also just state it explicitly too as 1 meter per second down or west or backward, depending on what the situation is. The instantaneous speed at 13 seconds. So 13 seconds is in this interval here. But this time, we're dealing with a speed, which is a scalar. The direction doesn't matter. So we can still find it by finding the slope of the line at that point, but we're going to take the absolute value to find the speed. So that gives us a speed of 4 meters per second. And again, we don't care about the direction for a speed because speed is a scalar. So 4 meters per second is a complete answer. The particle's instantaneous speed at 16 seconds. Well, at 16 seconds, it stops moving, right? The position doesn't change. So the speed is 0 meters per second. the average speed of the particle over the 20-second interval. So remember the difference here between average speed and average velocity. Average speed deals with total distance traveled divided by the total amount of time it took. So we found our total distance up here, number 3 is 22 meters. So our total time interval, 20 seconds, gives us 22 divided by 20, or 1.1 meters per second on average. But if we think about the average velocity, remember that deals with the displacement divided by the time interval. And our displacement is 0 because we ended up the same place we started. So we have an average velocity of 0 meters per second, even though our average speed was 1.1 meters per second. All right, hopefully you guys were able to answer at least some of those correctly in the time that I gave you. And so now let's think about the actual question, which was the velocity and acceleration time graphs. Okay. So when we're thinking through these graphs, I just kind of tried to sketch out what it looked like up top there for the position time graph. So we can see we have a bunch of different sections going on here, and we want to calculate the slope of each section to get the velocity time graph. So I divided it up into these sections, and if we find the slope at each section, that tells us about the velocity. So here we're dealing with a straight line, that means our velocity is 0. This part has a constant negative slope, so we're dealing with a constant negative velocity. This next portion is a constant positive slope that is pretty steep, so we'd have a constant positive velocity that is fairly high compared to the others. And we'll just move sideways along the graph in that same manner, just thinking about what the slope is doing at each portion and then thinking through what that means for the velocity. Similarly, to get the acceleration time graph, we'll look at our newly created velocity time graph and take the slope at each section, because the slope of a velocity time graph gives us acceleration. So in each case, we're dealing with a horizontal line in our velocity time graph. They're all at different places, but they're all horizontal lines. And the slope of a horizontal line is always 0. So our acceleration here is always 0 meters per second squared, or meters per second per second. Okay. Nice. All right, so we did a lot of stuff graphically dealing with positions and velocities and accelerations, how they all relate to each other. And so today I want to move into how they're related to each other mathematically, which really is an introduction to calculus today. So calculusly, they are related to each other. So if you guys have never seen calculus before, hopefully this will be a good introduction for you. If you have done calculus before, for example, if you took calc in high school, or if you did AP physics in high school, then these will probably be a review for you. But if this is brand new and it seems a little bit strange and awkward, feel free to ask me any questions or hang out after class to ask questions if you would like to do so. But anyway, when we're dealing with these quantities, right, position, velocity, acceleration, when we're dealing with them graphically, so far we've been finding the slopes of each portion of the graph and kind of related them down a stack of graphs, right? Position, velocity, acceleration, they're related to each other by the slopes. The calculus word for the slope of a tangent line is the derivative. I mentioned that the other day. We can also go kind of up the stack of curves, because if acceleration is related to velocity, then velocity is related to acceleration. And so when we go up the stack of curves, we're not taking the slope of a line anymore. We're taking something called the area under the curve, or the calculus word for that is an integral. So I'll be teaching you how to take derivatives and introducing the idea of an integral today, although integrals really are Calc 2 and Physics 2 predominantly. So you won't see them a whole lot in Calc 1 or Physics 1. So we'll just do a little introduction to those today. Okay, so when we're taking derivatives mathematically, there are a couple of rules that will need to be followed while we take these derivatives. So if you can remember these rules or write them down somewhere that's handy for you to access, that would be great. This is like the whole basis of Calc 1. Okay, so the first rule is called a power rule. And when we're applying the power rule, we'll multiply the coefficient by the exponent and then subtract 1 from the exponent. And it'll make a lot more sense when I can actually show you an example. So let's look at this example. Okay, the way we write out the derivative function is this kind of ratio, this fraction out front here, d over d something. That means take the derivative of the function with respect to a certain variable. So this would tell us the derivative of the function with respect to t, time. So whenever we see that variable t in the function, we'll apply this power rule, which says we multiply the coefficient by the exponent. So if we look at this function here, t to the fifth, the coefficient of t is this 1, which we didn't bother to write because 1 times t is just t. But we'll pretend that there's a 1 there out in front. The exponent here is 5. So if we multiply those together and write that out front there, 5, the exponent, times 1, the coefficient. Then we write our variable that we were taking the derivative with respect to, so t in this case. And then we subtract 1 from the exponent. So 5 minus 1 is our new exponent. So the derivative of t to the fifth using the power rule is 5t to the fourth. Okay, so again, that's the derivative of this function with respect to time. That gives us this result. Here's another example. This time we're going to take the derivative with respect to x. You can do it with respect to whichever variable you want, and it will always be kind of given to you in the setup of the derivative which variable you're going to be looking at. In this case, it's x. So here's our function, 3x squared. We're going to apply the power rule again, which is we multiply the coefficient 3 by the exponent 2. So 3 times 2 is our new coefficient. And then we write down our variable again and subtract 1 from the exponent, so 2 minus 1. So that gives us a result of 6x to the 1, or just 6x. Okay, here's another example. This time we're taking the derivative with respect to t, but there's no t in the function. It's just 15, just a constant. So when we're dealing with a constant and trying to take the derivative of a constant, it just ends up being 0, right? And think about this graphically too. Remember, a derivative is like taking the slope of a line. So if we have a graph of 15, so at every point in time, the value is 15, that means we're dealing with a horizontal line. 15, 15, 15, 15. And what's the slope of a horizontal line? 0, right? So the derivative of a constant is always 0. So like I was saying, you can take derivatives of any different variable that you want, and that initial fraction is going to tell you what the variable of focus is. And then if we have multiple variables in an equation or in a function, we'll just treat those other variables like a constant. This is called taking a partial derivative. So for example, if this is our function, xt to the fourth, You can see now we're dealing with two different variables, x and t, but our initial fraction tells us we're going to be taking the derivative with respect to t, not x. So we're going to treat x just like it's a constant, like it's part of the coefficient. So again, applying the power rule, we multiply the coefficient x by the exponent 4, and then we subtract 1 from the exponent on t. So our answer for this partial derivative is 4x t to the third. Okay. So this is probably the most helpful rule about taking derivatives that you'll be using in Calc 1 and Physics 1. This is kind of the fundamental rule of derivatives. There are additional rules which we'll go through momentarily, but this is the key one to remember, the power rule. Okay, so some other rules that I'll just kind of introduce to you. First of all, the sum rule. If we're dealing with a function that's two things added together, then here's how the rule kind of reads out. The derivative of the function f plus g equals, and here's this symbol, we call it f prime. That apostrophe means prime, and that's a symbol for derivative as well. So we take the derivative of the first part of the function and then add it to the derivative of the second part of the function. So f plus g, the derivative of that gives us f prime plus g prime. So here's an example. If our function here is x squared plus x cubed, the derivative of the function y with respect to the variable x would be, we can apply the power rule to both sections. So 2x to the 1, or just 2x, plus, and then applying the power rule to that second chunk, 3x squared. That would be the derivative of y with respect to x. The difference rule is very similar, right? The derivative of the function f minus g is f prime minus g prime. So here we have the function and we're taking the derivative with respect to v, and we have v cubed minus v to the fourth. So again, we'll apply the power rule to each of those sections, and we get 3v squared and 4v cubed, and then we just subtract those according to this difference rule. So those two are nice and simple, and we can apply these same ideas, these same rules, no matter what order or level of derivative we're talking about. So you can take the derivative of a derivative of a derivative of a derivative as many times as floats your boat, and we can still keep applying the same rules. So for example, here's our starting function. F of x is our function. So we have 5x cubed minus 3x squared plus 10x minus 5. Oh, a nice lengthy function to think about. If we take the first derivative, so just the derivative of the function, again with respect to x, because that's our only variable, apply that power rule to each chunk, and you can see here we're dealing with both a difference rule and a sum rule, as well as the kind of ubiquitous power rule that we already talked about. So this first chunk, applying the power rule, would give us 15x squared. This second portion, remember, multiply the coefficient by the exponent to get 6. Subtract 1 from the exponent to get x to the 1. Here, we multiply the coefficient by the exponent, which just gives us 10. And then when we subtract 1 from the exponent, we'd get x to the 0. Anything to the 0th power is 1, so we're left with just 10. And then remember, the derivative of a constant is always 0. So there's just this implied minus 0 that we didn't bother to write in here. But this would be our first derivative of this function. Now we can take the second derivative, and that's written by just giving it another apostrophe to show that it's the derivative of a derivative. And so in this case, we're taking the derivative of our first derivative function. So now we're looking at f prime x. So again, we apply the power rule to it. 15 times 2 gives us 30, and then 2 minus 1 is 1, so 30x to the 1. And then this next chunk gives us just 6. This 10 is now a constant, so the derivative of a constant is 0. That part goes away. So this would be our second derivative of the function. We could take the third derivative if we want to, right? Add another prime, keep on going, take the derivative of this function. In this case, it's just 30, applying that power rule. We could take a fourth derivative, although you'll see here that the notation kind of changes once we get up to that level of ridiculousness. And so instead of just continuing to add apostrophes, we just put the number of the derivative in parentheses up top there. This is not an exponent. This tells you which derivative you're taking. So the fourth derivative of the function. And since our third derivative is just a constant, the derivative of a constant is 0. So we could keep going if you wanted to. We could take a fifth derivative and a sixth derivative, but at this point, it's really meaningless because we just keep taking the derivative of 0, which is 0. And so from here on out, all of your derivatives would just be 0. But you can see we still just applied those same rules no matter what level of derivative we were talking about. First, second, third, fourth. We all use the power rule and these sum and difference rules. So I want you guys to give it a try using, again, that power rule, the sum rule, and the difference rule. And I want you to think through the following derivatives. So I'll give you guys a minute or so to work through these, and then we'll come back and talk through the answer. All right, so let's think through these answers together then. Okay, so our first part A, the derivative of this function, 12x to the fourth, with respect to x, that's our only variable. Again, we'll apply the power rule just like we had been talking about. So we take the exponent and multiply it by the coefficient. 12 times 4 is 48. We write down our variable again, x, and then we subtract 1 from the exponent to make it 3. So 48x cubed is the derivative of this function with respect to x. I wrote it in a different way here just because you'll see different notations as you go through physics and calculus. It means the same thing though, right? dx is the same thing as a prime. They both mean take the derivative of something. So if our function here, y equals 6x plus 1, that means the derivative of our function, or y prime, is just 6. Right? Again, applying that power rule and that sum rule gives us just 6 as our derivative. Okay. So for part C, here's our function x. X equals 2 minus 4t minus 4.9t squared. So the derivative of x, our function, with respect to the variable t, is another way of saying the velocity, right? If x is position, and we're finding the change in position over the change in time, that's the same thing as velocity. So the velocity is the derivative of position. And we found that graphically previously by finding the slope of the graphs. Now here we're finding it mathematically doing these derivatives. So since this first part is a constant, when we take the derivative, it'll go away. It's just 0. The derivative of a constant is 0. The next portion, 4t to the 1 becomes just minus 4, right? Because we multiply by the exponent 1, subtract to get t to the 0. So 4 times t to the 0 is just 4. And then here for this third chunk, we have minus 4.9t squared. Again, we take the exponent, multiply it by that coefficient to get minus 9.8, and then subtract 1 from the exponent. 2 minus 1 is 1. So this is our equation for the derivative, or for velocity. Now part C also asks you to find the second derivative. So if we take the derivative of the derivative, like we were doing previously, here's another way that you might see that written. So I had showed you on the previous slides, you could have it written as 2 apostrophes, like 2 primes. That means the second derivative. This notation is more common in physics. This also means the second derivative. So this little exponent up here tells you which number of derivative it is. This is the second derivative of the function x with respect to time. So it's a little bit confusing when it's written this way because we're not squaring time. This is not like an equation that we have to do. This is telling us we're taking the second derivative of this function, again, with respect to time. We didn't change the variable that we're taking it with respect to. It's again with respect to time. So that's why it has the 2 up there, again with respect to time. Well, previously, we saw the equation for acceleration, which is the change in velocity over the change in time, or dv divided by dt. So this second derivative of our position is actually the acceleration. And if we take the derivative of our velocity function here, the negative 4 goes away because it's a constant. The derivative of a constant is 0. And so we're left with just negative 9.8. Okay. All right. So there are a couple other rules for derivatives. I'm going to introduce them to you so you've seen them, and they will be helpful, as you go in physics and calculus. Yeah, so I want to make sure that you've seen them before you get into those classes. Okay, so the first of these other rules, I guess we have a lot of rules so far. So we have the power rule, the sum rule, the difference rule, the higher order rule. Now we have the product rule. So this is really our fifth rule of derivatives. So if we have a function that's two things multiplied together, the derivative of f times g is f times g prime plus f prime times g. Another way to just kind of say this rule is the first times the derivative of the second plus the second times the derivative of the first. And hopefully this will make a little bit more sense once I show you an example. So here we go. Here's our function f of x. We can see here we have two things, two kind of chunks multiplied together. So we have 6x cubed and 7x to the fourth. So we're going to call this first portion f and the second portion g so that it fits in this rule here, f times g. So f times g. So when we take the derivative of this function, applying the power rule tells us that we'll just rewrite that function f, don't change anything about it, and then take the derivative of that function g. So the d dx of that function g. Plus, the next chunk, we bring down that portion, that chunk we labeled g, don't change anything about it. And then we take the derivative of that chunk f, so d dx of f. So if we actually then apply the power rule to these derivatives, here and here, right, we still have 6x cubed. Now the derivative with respect to x of 7x to the fourth is 28, 7 times 4, 28. X, 4 minus 1 is 3, so 28x to the third. Plus, we didn't change anything about this term, we just brought it back down. The derivative of this function with respect to x is 18, 6 times 3, times x to the 3 minus 1, or 2. So 18x squared. So now if we multiply that out, right, 6 times 28 is 168. X cubed times x cubed is x to the 6th. Same deal over here. 7 times 18 gives us 126. X to the fourth times x squared is x to the 6th. And then we can add those things together to get a final answer of 294x to the 6th. Whew. These rules, while very, very helpful, take a little bit more practice, I think. So another rule is the quotient rule. If our function is a fraction, then we have to apply a different rule, the quotient rule. So if we want to take the derivative of this function that's f over g, then here's how it's written. And the way that it's often said, this rule, how it's said, is low d high minus high d low over the line and square the low. So in that phrase, the high refers to the numerator, the low refers to the denominator. So low d high minus high d low over the line and square the low. So here's an example. Okay, our function is a fraction, 4 over x to the 6th. So in our function, we're just going to label 4, the numerator, as f, and x to the 6th as g, so that it matches the way that the rule is written. So the derivative of this function, we do low d high, the derivative of a constant is 0, minus high d low. I applied that power rule, so the derivative of x to the 6th is 6x to the 5th, over the line and square the low. So x to the 6th times 0 goes away, it's 0. 4 times 6 is 24, but it's subtracted, so it's negative 24x to the 5th divided by x to the 12th. And we can simplify that a little bit more by taking out this x to the 5th on top and subtracting 5 from the bottom. So negative 24 over x to the 7th would be our final answer according to this quotient rule. Now, this example is, I think, a good one, because if you're clever, if you don't just jump right into it, but if you think about what function you're given, you might notice that there's a different way that you could write this that might make it a little bit simpler. So if we wrote this function as 4x to the negative 6, right? Whenever you have an exponent in the denominator of a fraction, you can write it as a negative exponent. So if we rewrote that as 4x to the negative 6, then we don't have to worry about the quotient rule. We can just apply the power rule. So according to the power rule, right, 4 times negative 6 is negative 24. Subtract 1 from the exponent, negative 6 minus 1 is negative 7. And that gives us the same final answer, negative 4x to the negative 7. I'm sorry, negative 24x to the negative 7 is the same thing as negative 24 over x to the 7th. So there are really two ways that you could have done this particular example, depending on how attentive you are and how creatively you can rewrite these functions. So I know that's a lot, especially for those of you who have never seen calculus before. But really, like what I just went over is basically an overview of almost all of Calculus 1. Like the whole class is basically about taking derivatives. So you'll get lots and lots of practice at this. There are, additional rules that I didn't go over for things like trig functions and inverse trig functions and gross things like that. I think they're gross. Maybe you don't, but whatever. So there are additional rules, but these are the ones that will be most helpful for physics. Um, so yeah, if you guys have questions, feel free to let me know, stay after class, that sort of thing. But we're going to keep rolling through this for now because I want to quickly introduce to you guys area under the curve, or the calculus term for this is integrals. Right, so we know from the past couple of days that position time graphs can tell us about the velocity. Right? The slope of a position time graph gives us the velocity. Well, that should mean then that the velocity time graph can give us information about position. If one is related to the other, then they're both related to each other, right? So the same thing for velocity and acceleration. If we can learn about the acceleration from the velocity time graph, then we should be able to learn about the velocity from the acceleration time graph. And we can. We just need to go about it in a little bit of a different way. Right? So far we've been going kind of down what I call this stack of graphs, down from position to velocity to acceleration. And we do that by taking the slopes or by taking derivatives. Same thing. If we're going up the stack of graphs now, so if we're going from acceleration to velocity or velocity to position, then we need to use a different process, area under the curve, or integrals. Okay, so here's a stack of graphs, right? We have a position time graph. Ooh, it looks like a roller coaster. And so we can go down from this position time graph to velocity by taking the slope of the line at each point. So we can see here in this first section, the slope is increasing, right? If you take your pen or take your finger and draw that tangent line along the shape of the curve, we see that it's increasing. So that means our velocity starts at 0 and increases. In this section, it's kind of a straight, not like horizontal, but like a straight line. It's increasing consistently. So the slope of this line would give us a constant velocity. It's got a constant slope in this section. In this middle section, we can see that it's getting less and less positive. So it's approaching 0 and then getting more and more negative. So our velocity graph approaches 0 and then gets more and more negative. This section right here, we have a negative slope. And as we move along, it gets closer and closer to 0. So a negative velocity that gets closer and closer to 0. And then this last section is a horizontal line. So the slope of that portion is 0. Right? Similarly, we can go from velocity to acceleration. So the slope of this section is a constant positive number. The slope of this section is 0. The slope of this whole section is a constant negative number. The slope of this section is a positive number. And the slope of this section is 0. Right? So that's how we would go down the stack of graphs like we had been doing before. But if we take a look at the units of our graph too, that should give us a clue as well as the information we can get from this graph. Right? So we know that slope is the change in your y variable divided by the change in your x variable. So in this case, delta x, the change in x over the change in time, would be meters divided by seconds, and that's the unit of velocity. Right, so similarly, meters per second divided by seconds is meters per second squared. That gives us acceleration. Now, if we're thinking about the area under a curve, not the slope anymore, but the area, the way we find an area of a triangle is 1/2 base times height. The way we find an area of a square or rectangle is base times height. So the base, the x unit in this graph is time, so seconds, times the height unit, meters per second. So meters per second times seconds gives us meters. And that's the unit of position. Well, really here, displacement. So we're dealing with a change in the position. So displacement. Right, so these things are all connected to each other. We can go down and we can go up. So when we're taking the integral, or another word for it is the antiderivative, because you just do the opposite thing that you did for a derivative. Um, like I said, we're not going to go into a whole lot of detail. I'm not going to go through all of the rules of integrals with you, because that's Calc 2 and Physics 2, not really Physics 1. But basically, graphically, what an integral does is figures out the area under a curve. And I don't really like the phrase under the curve. I think that's a little bit misleading, because it's really talking about the area between the the line, the curve, and the x-axis. So if we look here, this pink shaded area is the area under this curve. So the area between the line and the x-axis. But in this case, the area under the curve here is actually over top of the line. It's just the area between the line and the x-axis. So over here, it's above the x-axis. Over here, it's below the x-axis. But those pink shaded regions are what we're referring to as the area under the curve. So some helpful formulas to remember. The area of a rectangle or a square is base times height. So whatever the base length is times whatever the height is. The area of a triangle is 1/2 base times height. The area of a trapezoid is 1/2 the small, they call it a base, but it's really like the top, a small line, plus the bigger base times the height. Okay, so those three formulas are going to be really helpful to remember. All right, and so over here in this box, I just have the calculus ways to write these relationships. So the derivative of a position time graph gives us velocity. The derivative of a velocity time graph gives us acceleration. This swirly thing is the integral symbol. So the integral of acceleration time graph is the change in velocity. And the integral of a velocity time graph is the displacement, the change in position. Okay, so I know we just have a couple of minutes left, but I want to go through a quick example with you so you can see what I mean by area under a curve. So here we have a velocity time graph, and we want to find the change in position, or the displacement, after 5 seconds, after 10 seconds, and after 15 seconds. So in this blue box, I have a really key thing for you to remember. We cannot find the instantaneous position. We can just find the change in position. Sorry, I have a question here from Aaron. What are the top and bottom numbers next to an integral symbol? So hold on. So like here's our integral symbol. And usually in calculus, we'll have like a number here on the bottom and a number here on the top. Is that what you're referring to, Aaron?
Yeah.
Okay, so that would tell us um, kind of the same thing that this example is telling us. It tells us the sort of time frame that we're interested in, the area under the curve between these, they're called the bounds of integration. So that would tell us, in this case, between 0 seconds and 5 seconds. So you would see here between 0 and 5. That's the area that we're looking at. Does that make sense?
Yeah, thank you.
You're welcome. Good question. Okay. So our first time interval here, this first 5 seconds, is a rectangle, well, I guess really a square in our graph. So we're going to apply the equation for the area of a square, base times height. So this base is 5 seconds. The height is 5 meters per second. So that gives us a displacement there of 25 meters in that first time interval. The next time interval is all the way to 10 seconds. So we know what it is for the first 5 seconds. Now we're going to figure out what it is in this next from 5 to 10. And that's a triangle. So we're going to use the area of the triangle equation, 1/2 base times height. In this case, our blue triangle, the base is 5, because it goes from 5 to 10 seconds. The height is, again, 5 meters per second. So 1/2 of 5 times 5 is 12.5 meters. And so that's, again, just for that little portion from 5 to 10 seconds. But if we wanted to find the change in position after 10 seconds from the beginning, then we would just add those two areas together. So 25 plus 12.5 gives us 37.5 meters so far. Now, after 15 seconds, there really is no area to find because there's no distance between the curve and the x-axis. The curve is literally sitting on the x-axis. So the height of our rectangle here is 0, which means the area is 0. There's no area under this curve because it's right on the axis. So that means our total displacement over this whole 15-second time interval is 37.5 meters. Okay. So when we're dealing with graphs that are like linear sections like this, it's nice and simple to take the integral. All you have to do is find the area of each little section and add it together. When we start dealing with curves, like actual curved lines, that's when we would need some of those integral rules. But I won't give you any examples like that because, again, that's really more Calc 2 and Physics 2 than you'll get into in Physics 1. But before I move on to, I think, one more example, I know I just have a couple minutes, but I want to get through one more example. So if the curve is beneath the x-axis, it is totally possible to have negative heights, which just like makes you cringe a little bit, just instinctively, like, oh, it's so unnatural having negative heights. But it's totally fine in physics, unfortunately. Okay, so here we go. I want you guys to try to find the total displacement of this object over that whole 18-second time interval. So I will say that there are a couple of different ways that you can do this, but what you're going to want to do is find the area of this section and the area of this section. So you could either use the trapezoid area equation, or you could break it down into rectangles and triangles and do it that way. You'll get the same answer either way. But take just a couple minutes and try to figure out what the total displacement of this object is over that full 18-second time interval. All right, so I know that was a really quick minute. You probably didn't get a chance to finish the whole thing. That's okay. I wanted to make sure we had time to go through the answer before you guys leave. So again, two different ways you can do it. The first way, I'll go through both methods just so you can see them. But the first way is to use the area of a trapezoid equation. So 1/2 base plus base times height is our equation for a trapezoid area. So 1/2, this little base is 4 seconds. This bigger base is 6 seconds. So 4 plus 6 is 10. And then the height here is -12. So the area of this section of the graph is -60 meters. And again, it's totally acceptable to have negative areas. Ugh, awkward. Okay, and then we have this other trapezoid over here. So again, our equation is 1/2 little base, so 4 plus big base, 12, times the height, 18. And so the area of this trapezoid is positive 144 meters. So we have -60 meters plus 144 meters. That gives us a total area or a total displacement of positive 84 meters. Now, I wrote this out the second way. If you forget the equation for the area of a trapezoid, you probably remember the equation for area of a triangle and area of a rectangle. So you can just break it down into more sections. Right, here's our first rectangle, find that area, find the area of this little tiny triangle, find the area of this triangle, this rectangle, this triangle, add them all together, you still get positive 84 meters as our total displacement. Okay. So I think next, I want you to describe in words what the object is doing. We'll go through that tomorrow. So we'll pick up at this place tomorrow. But thank you guys for sticking it out with me for an extra couple of minutes. If you guys have questions, I'll stop the recording so you guys can ask your questions. But otherwise, I hope you guys have a lovely day and I will see you tomorrow. Bye.